All right, everybody. Welcome back. So I'm really sorry I've been away for a while. I've been working on getting some data for a grant application ready, and it's just not been working out well. qPCR is easy to do, but trying to design primers and stuff is not, I guess, especially when you have to go across junctions. Anyway, so today I wanted to do a quick, hopefully short, QC check of the microbial contamination and the RNA contamination that we had looked at last time. And then also we can run FeatureCounts as well and get the read counts for all of the genes or transcripts that we had mapped when we had used STAR. So the first thing that we have to do is get to our P53 folder. If we look in here, we'll see we have our rRNA contamination folder as well as our microbial contamination folder. So if we go into our microbial contamination folder, we have all of our outputs and our reports. And the nice thing about the later versions of of multi-QC, it actually can look at the output of Kraken and make that really nice report. But in this case, I think for multi-QC and Kraken, it's super basic. But let's take a look at it. We can do multi-QC and then dot, and that'll look through all the files in this folder and find a report file or the output. So here it goes. Found 12 and it's done. So if I go into my browser, microbial contamination, there we go. So let's look at Firefox now. So here's the output for the microbial contamination. It's super basic. We can get really far into it too. But the important thing here is this top part. We're going to look at, like we mentioned last time, we have 3.5% mapping to Homo sapiens, and then the rest are unclassified, as well as some of the microbial. So on here we have Homo sapiens is the blue. We can look at phylum. So the gray are going to be other, and then unclassified. But so the good thing here is that a large proportion of the unclassified, or a large proportion of these of the reads are unclassified. Homo sapiens is a small percent. And if we remember, these are the output files from STAR that didn't map when we used STAR. So these are already ones that didn't map to the mouse genome. So this is just double checking that we're not getting too much contamination, I guess. All right, so if we go back to Ubuntu, we can then navigate to our rRNA contamination folders. If we go up and look again, so we're going to change the directory to rRNA. And here are the output files, the 12. We can do multi-QC. I'll run this one. Should be pretty quick as well. Here we go. And let's switch back to Firefox. There we are. So here we're looking at millions of reads mapped. Might be easier to look down here. So the total reads and the total that passed QC, and then the amount mapped. So here we can see that there's a really low proportion of the total reads that actually mapped to our RNA file that we made, which is good. We don't want the number of mapped here to be really high. That means we have a high proportion of rRNA, and we're not going to get a whole lot of quote unquote information from that when we're looking at differentially expressed genes, since our RNA isn't going to tell us whether or not a gene is up or down regulated. So now that we have our contamination QC looked at, we can go ahead, we'll back out of here. We have to get into our environment now. So you can do conda, activate, tutorial environment. There we go. So we have our contamination done. Now we can move on and look at counting our features. So when we aligned with star, we aligned our reads to the different locations depending on the annotation file that we also had fed in. So now we have to go through and count what feature or what transcript, gene, whatever we want to tell it, what gene each of those reads that mapped are actually mapping to. And then later on we can go and analyze the different genes and everything like that. So the tool that we're going to use today is called FeatureCounts. And FeatureCounts is part of a larger package called Subread. So we can do conda install Subread. And hopefully this goes rather quick. So yes, we want to install Subread, and also OpenSSL will be updated. There we go. So we can clear again. So we start typing feature counts. We can autofill it with tab. And in here we have some things that we want to tell it. If we scroll to the very top of our help, we can do it just by typing feature counts. We can type feature counts -h. And we have some things that are required. So first is going to be our -a. So this is the annotation file that we used to one, build the star index, and then two, also use star to map the reads to the genome index that we created. So you have to feed in that same GTF file that we have. It can also be GFF. And we have to make sure that it's the same thing. We can't use a different version of the genome or anything like that at this point, since we already started with a particular genome version and GTF version. We have to stick with it all the way through. -o is going to be an output. So that's where we're going to tell it, okay, put the results that you find in the read count table here, as well as the summary. Another thing that we're going to input is going to be -t, which is the number of threads. And that's down here somewhere, big T, yep. As well as -g. And what -g is, it's going to tell what part of the GTF file we want to keep. So in our case, we have kind of a list of things. If you open up the GTF file, you can see in there, let's see, we change directory to musculus and CVI build annotation archives archive 2015 40, and then we want the genes, and then genes GTF. We'll go here, and then we'll look at the head of our genes GTF. So in here we have exon, or the coding sequence, a bunch of different information, starting, ending, positive strand, negative strand. But on the right hand side, this is where our -g is going to come in. So gene ID, I don't know why it doesn't work, but we can always get back to the gene ID from transcript ID. So what we're going to do when we look at our -g is we're going to input in quotes input transcript ID. So that'll tell us which version of the transcript we're actually going to collect. So let's get back out of here. And we're just going to actually copy this. Make it easier. Okay. Now let's make a directory for our output of our counts. So we'll call it make directory read counts. We can feed our output from FeatureCounts into that. So, whoops, lowercase FeatureCounts dash big T, and we'll go like 8 cores, something like that. Dash A, and this is where we're going to have to tell it this location. And then genes. That's our GTF file that we want to use. In addition to that, like I said, we have to use -G and then transcript underscore ID. And that will tell FeatureCounts to look for the read. If the read is in here, then we're going to take this and we're going to keep track of it. Okay. So then -O will go into our read counts folder, and then we'll output read counts.txt or something like that. Just a generic name that we can always go back later and know what we're looking at. Finally, the last part, we don't have to put a flag in for it. We can just tell it star aligned and then star-BAM. That's going to go into our, let's see, star aligned folder, and it's going to look for all of the, whatever star is the wild cards. It's going to look for the beginning, can be whatever, and then the end is .bam. That's going to tell read counts, this is the file that we want to look in to find out whether or not the reads are part of these particular features or transcripts. So we go ahead and run that. It's going to start, it'll take a little bit to get going. Okay, so now FeatureCounts is finished. Go into our read counts folder. Run multi-QC and see what we get. So it found our 12 reports within our file. And now we can open it up. Switch to Ubuntu, or from Ubuntu to multi-QC. So you have a percentile assigned. Remember, we were only telling it to look for transcript IDs. And then the million of reads that were assigned. There we go. Down here we have proportions. So there were some, like this one, that had really low number of reads in comparison with something like 778. 787 had a lower number, but if we come up here, 35% and 787, 35.4. About the same percentage, which is good. So that should do it for this time. Next time we can look at loading it into R and just kind of prepping the R environment for everything that we're going to need. So that should do it. Thanks.